Okay, in this lecture we're going to finish our section 4.1 material on vector spaces and subspaces. Now the last part of this section has to do with a subspace which can be considered as being spanned by a set of vectors. So a little terminology that we'll use throughout this chapter is similar to what we've seen in chapter 1. So when we refer to a linear combination of a set of vectors of a vector space, we're referring to any sum of scalar multiples of those vectors from some vector space. So something of the following form. Let's take the sum of scalar multiples of vectors v1, v2 up through vp, where the scalar multiples, or the scalars that we're multiplying those vectors by, are the constants c1, c2 up through cp. Now similarly, the span of a set of vectors v1 through vp from a vector space, which is denoted as span of v1 through vp, would refer to the set of all vectors that could be expressed as a linear combination of v1 through vn. So that would be the set of all vectors, let's say vectors of the form A, that could be expressed as a linear combination of these vectors v1, v2 through vp. So we have the following result for this span of a set of vectors. So this is Theorem 4.1 from your textbook, which says if we have a set of vectors v1 through vp, which are elements of some vector space V, and we have a set H, which is the span of the vectors v1 through vp, that is the set of all linear combinations of those vectors, then that set H is a subspace of V. So in other words, the set of linear combinations of vectors v1 through vp is a subspace of the vector space V that those vectors were taken from. So let's consider the proof of this theorem. We know that there are three things we need to show for a space to be a subspace. The first is that it contains the zero vector for that vector space. Now in this example, or in this case, we can say that clearly 0 is in the set H, since the 0 vector could be written as a linear combinations of v1 through vp by taking each scalar to be 0. That is, if we were to take 0 times v1 plus 0 times v2, and so on, up through 0 times vp, we would get the 0 vector, and it's a linear combination of these vectors v1, v2, vp, so this is an element of H. So 0 is within our set H. The second condition that we need for subspace is that it has to be closed under vector addition. So let's choose two vectors in the set H. So let's call them maybe x and y, which will be elements of this set H. Now, since H is the span of a set of vectors, and x and y are elements of that set, that means that both x and y have to be linear combinations of the vectors v1 through vp. So x we might write as a1 times the vector v1 plus a2 times the vector v2, and so on, up through ap times the vector vp. And y we could write as another linear combination. Let's say b1 v1 plus b2 v2, and so on, up through bp vp. So if we consider the sum of these vectors, say x plus y, then we would have the sum of these linear combinations given above, and by rearranging the terms in that summation, which we can do by using the associative property of, or commutative property of vector spaces, we could combine the terms a1v1 and b1v1 and write this as the sum of the scalars a1 and b1 times v1. So here we're making use of the commutative, associative, and distributive axioms of vector spaces. Now, we could then combine the terms involving the vector v2 using the same properties, and we would have a2 plus b2 times the vector v2, and so on, up through combining the terms for the last vector vp. We would have a scalar ap plus bp times vp. So the sum of these two vectors, x plus y, is, as we can see here, a linear combination of the vectors v1, v2, up through vp. So it's the sum of scalar multiples of each of these vectors, where the scalars are a1 plus b1, a2 plus b2, and so on. So this illustrates that the sum x plus y is in H, since it's a linear combination of those vectors. So the last condition that we have to show that something is a subspace is that the space is closed under scalar multiplication. So let's choose some scalar. Let me maybe call it r in the real numbers. And let's choose some vector x from H. So some linear combination of the vectors v1, v2 through vp. So if we look at the scalar multiple r times x, well, using the distributive property of scalar multiplication for a vector space, we would have r a1 times v1 plus r a2 times v2, and so on up through r ap vp. So here we see that the scalar multiple r times x is again a linear combination of the vectors v1, v2 up through vp, where the scalars are r times these a1, a2, and so on. So that means that this scalar multiple is an element of H. It is within that span. So we've shown all three conditions for a subspace hold, which means that H is a subspace of the vector space V, where our vectors v1 through vp were chosen from. All right. So a little terminology to go along with this result. We would say that the subspace, which is the span of v1, v2 up through vp, is called the subspace spanned by, or the subspace generated by, the vectors v1 up through vp. And given a subspace H of a vector space V, we would say that a spanning set, or a generating set for that subspace, would be a set of vectors v1 through vp, such that H is the span of those vectors v1 through vp. All right. So let's look at a couple of examples making use of this theorem. In this first example, we are told that H is a set of all vectors of the form 2t, 0, negative t, and we're told to find a vector v in space, that is R3, such that H can be considered as the span of that vector. And then we're asking the question, why would that show that H is a subspace of R3? So here, H is the set of all vectors of this indicated form. And we notice that we could think about this vector as being the set of all scalar multiples of a single vector. So in particular, I notice that each component of this vector involves a t term. So I could think about H as equivalently as the set of all vectors of the form t times the vector 2, 0, negative 1. If we were to distribute that t coefficient to this vector, we would have exactly 2t, 0t, and negative t. So another way to think about the set of vectors is in this way. It's the set of all multiples t of this vector, which we will call v, such that t is any real number. So that is the span of this vector v that we've identified. So if we let v equal the vector 2, 0, negative 1, then we have established that our space H is the space spanned by this vector v. And our new theorem, theorem 4.1, we know that any space spanned by a set of vectors is a subspace. So H is a subspace of R3 here. All right. So we found the vector v that we were interested in, such that H can be written as the span of that vector. And by theorem 4.1, that spanning space must be a subspace of R3. So in our next example, we have a very similar problem. We have a set W, which is a set of all vectors that have the following form, shown here. And we're supposed to find vectors u and v such that W could be considered as the span of the vectors u and v. And then we ask the question, why would that show that this set W is a subspace of R4? So as we did in the previous example, we noticed that this general vector, each term in this general vector involves s's and t's. So we could think about rewriting this set W in terms of a linear combination of two vectors involving s's and t's. So if I were to consider factoring out an s from each term of this general vector, the coefficient for s would be 1, 1, 2, 0. So we can see that by looking at our elements here. We have 1s, 1s, 2s, and 0 s's. Now to capture the terms involving t, I could take t, or the sum of t times, let's look at the coefficient for t in each element. We have 3t, negative t, and 4t. So I'm multiplying t by this coefficient vector, 3, negative 1, 4. So W is the set of this linear combination of two vectors, which I'm going to call u and v, such that s and t could be any real numbers. So if we were to let u be the indicated vector here, 1, 1, 2, 0, and v be the indicated vector 3, -1, -1, 4, then our space W could be considered as the space spanned by the vectors u and v. So according to Theorem 4.1, W is a subspace of R4. All right. Okay. So in this next example, this one's sort of similar to your homework problems. We're given a set of vectors v1, v2, v3, and w, which are vectors in R3. And we're asked a few different questions. In part A, we're asked first, is w in the set of vectors v1, v2, and v3? So when we are looking at this set, the set of vectors v1, v2, v3, this is not the same as the span of that set of vectors. It's just the collection of vectors v1, v2, and v3. Now we see that w is different from v1, v2, and v3. It's not equal to one of those vectors. Therefore, w does not lie in the set of those three vectors. So we can say no, w is not an element of the set v1, v2, and v3, since it's not equal to one of those three elements. So then we ask the question, well, how many vectors are in the set v1, v2, v3? So here we have a set where each element is given explicitly. We see that there are three vectors in this set. Here there are three vectors in the set v1, v2, v3. They're listed explicitly there. Now in part B, we are asked the question, how many vectors are in the span of v1, v2, and v3? So recall here the span of this set of vectors, v1, v2, v3, would be the set of all linear combinations of those vectors. So vectors which would be a linear combination of v1, v2, and v3, where these coefficients c1, c2, c3, or I'll call it just ci in general, could be any real numbers. So since we're considering all possible linear combinations of these vectors, well, that means c1, c2, and c3 could be any of the infinite number of real numbers, which means that there are infinitely many vectors in that span. So there are infinitely many vectors in this span of v1, v2, and v3. All right. And in the last part of this example, we ask the question, well, does the specific vector w lie in the span of v1, v2, v3? We know there's infinitely many vectors in that span. Here we're asking, is w one of them, and why? So let's consider the problem we're asking here. We want to know, is w equal to some linear combination of the vectors v1, v2, and v3? So this vector equation, we know that we could write in matrix form as some matrix A times a vector C is equal to W, where this matrix A has the vectors v1, v2, and v3 as its columns. So that's from the definition of multiplication of a matrix times a vector that we saw from chapter 1. So we want to know whether this system of equations written in matrix form, A times C equals to W, has a solution. Now to answer that, let's consider an augmented matrix. So here the augmented matrix for the system would be the matrix where, first off, A has v1, v2, and v3 as its columns. So our first column is 1, 0, negative 1. Second column is 2, 1, 3. And our third column is 4, 2, 6. So then setting this equal to a vector W, so augmenting this with W, which was the vector 3, 1, 2. So to see whether we have a solution, we can perform row reduction on this matrix. And we see that in our first row, we have a leading coefficient of 1 with a 0 below it, and we need to eliminate the negative 1 in our third row. So to do that, we could take row 3 and add row 1 to it. So our first row remains 1, 2, 4, 3. Our second row is now 0, 1, 2, 1. And then adding the first row to the third, we have 0, 5, 10, 5. So now our first column is exactly what we want. We have a leading 1 in the first row with zeros below it. The leading entry in my second row is a 1. And to try to move this towards reduced row echelon form, I want to eliminate the 2 that appears above that pivot and the 5 that appears below. So let's see how we could do that. For row 1, I could take row 1 minus 2 times row 2. So my second row I'm going to leave alone at 0, 1, 2, and 1. And that makes my first row 1, 0, 0, 1. And then to simplify in my third row, I could take row 3 minus 5 times row 2, which gives me 0, 0, 0, 0. So here we have a coefficient matrix, which was 3 by 3. It only has 2 pivot columns. So my third variable, in this case C3, will be a free variable. So let's see if we can find our solution from this augmented matrix. We find that using our first row, 1 C1 is equal to 1. Using our second row, we have 1 C2 plus 2 times C3 is 1. So C2 is 1 minus 2 C3. And C3, which was our third variable, is going to be a free variable. So now we can make some choice for C3 to get a specific solution of our equation. So if we were to choose, for instance, C3 equals to 1, we would have C1 is 1. So for our linear combination that we're considering here, C1 is 1 times V1. If C3 is taken to be 1, then C2 is negative 1. So we've got negative 1 V2. And then plus C3, which we chose to be 1, times V3. And that would be equal to W. So we've shown that the vector W can be written as a linear combination of these three vectors, which means that the vector W is in the space spanned by the vectors v1, v2, and v3. All right. So in our last example, we are given the following. We're told to let W be the set of all vectors that have the general form shown below, where A, B, and C we're told represent arbitrary real numbers. So in each of these cases, we're either supposed to find a set S of vectors which spans our space W, or we're supposed to give an example to show that W is not a vector space. All right. So in our first example, part A, we're looking at the set of all vectors W that have this arbitrary form. And we could try to write this vector as a linear combination of vectors by looking at the coefficients for these arbitrary real numbers, A, B, that appear within our vector. So we could express this vector as the sum of A times, if we look at the coefficients of A in each entry, we have -1, 1, 1, plus the arbitrary real number times, if we look at the coefficients for B in each entry, well, we have 0B in the first entry, -6B, and 2B. So we have 0, -6, 2 as the vector that we're multiplying by this arbitrary number B. Now we notice that there's one term left over. In this first entry, we had a constant 1. So we are then adding a vector 1, 0, 0. So here, this set of vectors, well, we see it's a linear combination of two vectors. It's any scalar times this first vector, plus another arbitrary real number, B, times the second vector, and then plus a specific third vector, 1, 0, 0. We're not multiplying by any arbitrary number there. So the fact that I'm always adding a vector 1, 0, 0 onto the end of this linear combination makes me suspect that I might not be able to hit the 0 vector, or the 0 vector is not contained within this set W that's being described. So let's ask ourselves, is the 0 vector an element of this space W? So to try to determine this, let's set the vector -A plus 1, A minus 6B, and 2B plus A equal to the 0 vector. We know in order to be a subspace, or a vector space, we must contain the 0 vector. So let's see if that's possible here. Using our first equation, in order for -A plus 1 to equal 0, we would find that A has to equal 1. Now if A is equal to 1, let's look at our second two equations. Or in order for my second components to equal to each other, A minus 6B has to be 0. Now A is 1, we found, so we would have 1 minus 6B is 0, which implies that B would have to be 1/6. Now, let's see if those values of A and B solve this third equation, 2B plus A equals 0. So if we have 2b plus a for the values we found. Well, 2b would be 1/3 plus a, which is 1. We can see that's 4/3, which is not equal to 0. We've shown that the 0 vector is not an element of the set W. W is not a vector space. All right. Now in part B, we have a 4-dimensional vector, and we see that each of our entries involves an arbitrary real number, A, B, or C. So we could maybe try to write this general vector in terms of a sum of vectors involving A, B, and C. So let's start with the terms involving A. Looking at the coefficient for A in each term, if we factor out an A, we're left with coefficients of 4, 0, 1, -2. Plus, if we look at the coefficient of B in each term, we have a vector B times 3, 0, 1, 0. And then plus, if we look at the coefficients of C in each term, well, we have 0C, 0, 1, and 1. So we have a vector C times 0, 0, 1, 1. And that captures all of the terms in the set W. So we see here that our space W can be written as a linear combination, that is a sum of constant multiples of these 3 vectors. So let's give these vectors names. Let's maybe call these V1, V2, and V3. So we have shown that our space W, which is filled with vectors that have this general form, can be considered as the space spanned by the vectors V1, V2, and V3. So according to Theorem 4.1, W is a subspace, so therefore it is a vector space. All right. So in this last part of our section 4.1, we've established that a set of linear combinations of vectors from a vector space is a subspace, which is referred to as the subspace spanned by those vectors. And the vectors which span that space are called a spanning set or generating set for that subspace.